So separation of variables is great. It doesn't work in a lot of cases. You've got to be able to actually separate your variables. And you're only really allowed to work with multiplication and division. So honestly, if I kind of looking at this problem at first, I would take a second and kind of scratch my head and say, could I actually separate these variables? And it does turn out that you can separate these variables because both of those terms have an x in them. So you can factor that x out, which is going to cause basically you to have a multiplication. That's really the key. You can't separate variables by like bringing 4x to the other side, because then you're not going to be able to split the dy dx on both sides. That's really what's going on. You really need dy dx isolated when you bring the dx over. But because you can turn this into multiplication, I'll take a 2x out. Why not? That should give me y plus 2. And now that I have multiplication, I can divide both sides by y plus 2. So that will give me dy over y plus 2 equals 2x dx. So just that's the important part about this example, is understanding that there's never a time where minusing 4x is going to work there. You just won't be able, whatever you do, when you bring the dx over, it will be incorrect. So you might do something, it might feel like you're on the right track, but it will not be algebraically correct. So now we integrate. Never leave this line as is, because this is the language of integrals. So boom. Integral of dy over y plus 2 is, it is. It's just a horizontal shift, so it works just like a y. And then that's going to equal x squared plus c. So again, this actually follows the pattern to the left, where we're going to exponentiate both sides, which is going to give us absolute value of y plus 2 equals e to the x squared plus c. And that plus c at the end is really a constant coefficient out in front of the c. That's what we did in 2 steps that I crossed off yesterday. So the next line here looks like we lose the absolute value bars because we're actually getting a plus or minus on the other side, but we're putting that in front of the capital C. So we don't need that plus or minus. C can be any number in the world. Putting a plus or minus in front of that number doesn't change the fact that it could be any number in the world. So that's how we lost the absolute value bars. So we end up with y equals c e to the x squared minus 2. Okay, so like I said, I'll give you about 20 more minutes. We'll go over the back of this one. We'll write down the patterns, and we'll do the 3 examples for the next lesson. Okay, so like I said, there's kind of some patterns that we see here. This just kind of summarizes it. I don't know if we had any examples where after we separated our variables, the left-hand side was just dy. But if I take the integral of dy, what do I get? Y, yeah. So if you're ever in a situation like that, life is easy, because you just get y equals and there's no solving technique. You're just done. I mean, but this would be a situation that we could have handled back when we first learned integrals, because you would just be doing things in terms of x on the other side. Okay. So we have dy over y next. When I integrate that, what do I get? ln absolute value of y. Yep. All right. Yep. All right. From there, we're going to, just a day of fun words, exponentiate both sides. Bring the c out of the exponent. And lose the absolute value bars. Again, because the way you lose absolute value bars is by putting a plus or minus. You're putting that plus or minus in front of a number that could be anything. So it's not serving any purpose. All right, next example is y dy. When I take that antiderivative, what am I going to get? Yep, y squared over 2. So obviously I have to multiply both sides by 2. You can leave the c alone when you do that. And then you've got basically y squared equals, so you have to square root both sides. And you need a plus or minus in front of that square root. But don't forget plus or minus. Notice I didn't leave the c alone there because that c has to get square rooted as well. You've got to square root the whole sum that you end up with there. So you only get to leave the c alone when you're doing simple things to it. All right, next one, dy over y squared. When I integrate that, I'm going to get, 1 over y. Not 1 over y, but negative 1 over y. Yep. So obviously, just like the other one, the first thing to take care of is multiply both sides by negative 1. And then you're going to reciprocate both sides. And that means you really need to do 1 over everything you see. So I'll put that here as a note, 1 over everything you see. Or just 1 over everything. So that c ends up in the denominator. You can't just like say, oh, I'll just 1 over c. That could be any number. That's not how this one works. You need to take the whole side and reciprocate. All right. And then the last common pattern that we see is e to the y dy, the world's easiest antiderivative, e to the y. And to solve that, you need to ln both sides. You are not taking an antiderivative, so no absolute value bars. We kind of just get in like this habit of like, oh, it's ln, so there has to be absolute value bars, except that's not how it works because you're not integrating. All right. So again, just the common patterns. Is that to say that you can't have dy over y cubed? No, that could happen. You just have to problem solve at that point. So dy over the square root of y? No, that can happen. There are other things that can happen, and you may just have to problem solve, but these are the ones that, you kind of see the most. All right. So with that, we will jump into G6, which I definitely remember opening, yet somehow isn't here. Oh, yep, there it is. I never actually opened it. That's what it was. Okay. All right. Okay. All right. So when it comes to solutions for differential equations, there's 2 different words that we have. In G5, we were finding general solutions. We had a variable, a parameter, something that's a number we just didn't know. Changing that parameter changes the curve. For every individual number you plug in for that C value, you get a different curve, and each of those curves are a particular solution. So if you know 1 point on your solution curve, you can pinpoint the exact curve that solves your differential equation. So a lot of these are going to be just doing what we did in the last practice with just one extra step of finding, what that C value is. So Here we go. We've got find the solution to dy dx equals x squared, xy squared, the quantity, with initial condition y1 equals 1. So some slope fields are included here. The curve that we're going to get should follow that slope field, which means that when we plug values a little bit bigger than 1 in, this thing should shoot off to infinity, right? As you can see that that's sort of what's going on there. This curve should flatten out. And it looks like I'm actually going to go down and curve out like that. I could do better. Definitely has a horizontal tangent. It decreases and it tangents back on like that. So we'll graph this solution that we get in Desmos and verify that it does look like that. You can see, especially on my screen, I don't know how it looks on your paper, there are definitely vertical lines on top of that x-axis there. All right. So we have to separate our variables. Xy squared is the same as x squared y squared. So we end up with dy over, so we end up with dy over y squared when we divide it equals x squared dx. Don't leave that alone because that's the language of integrals. So we integrate both sides. We just talked about this a minute ago. That gives us 1 over y on the left and x cubed over 3 plus c on the right. Calc is easy, right? You guys all knew that. So we are going to reciprocate both sides and multiply by a negative in not that order. So let's say 1 over y equals negative x cubed over 3. I'm going to leave it as plus c. If you had accidentally changed it to minus c, you'd just get your sign would be different than mine, but in the end, your function would match. So we end up with y equals 1 over negative x cubed over 3 plus c. That is the general solution. Every curve you could possibly draw on that slope field would match that equation, just perhaps with a different c value. Okay, next part. We just need to solve for that c value. So they're telling us that the y of 1 is 1. So the y of 1 is 1. And that is also 1 over negative 1/3 plus c. Yep. So there's a couple ways to solve an equation like this. I think the easiest way to think about it would just be to cross multiply. Knowing that another way to think about it is knowing that they both have the same numerator, I could just set the denominators equal to each other. But they're both going to give me the same result. If I cross multiply, I'm going to get negative 1/3 plus c equals 1 equals 1. Agreed? Okay. Yep. So it sure sounds like c equals 4/3. Cool. All right, let's see what this curve looks like. I'm cautiously optimistic. That negative sign is worrying me a bit, but we'll see. Desmos. Y equals 1 over negative x cubed over 3 plus 4/3. Cool. Yep. Now, one of the things, yeah, that sure looks like it, doesn't it? One of the things that has happened here is we actually have more in this than we would have in reality. So the actual solution is only the left-hand side of the curve. So whenever you asymptote out like that, I'm going to put on the end of that solution that x, I'm going to kind of put a restriction on the domain that x has to be less than 1. I say this, I don't think I've ever seen like an FRQ where you've had to come up with that idea on your own, but just know that in case you saw some extra information in like a multiple choice question. So we don't go over discontinuities, and there is an infinite discontinuity there at x equals 1. So I'm just going to add that to my answer. So my answer is y equals 1 over negative x cubed over 3 plus 4/3, and x is less than 1. Is that, wait, did that asymptote at 1, or am I actually getting that wrong? But the y of 1 is 1. No, it's it goes further. Yeah, no. Yeah. I guess we'd actually have to solve it. Okay. All right, in that case, I'm going to leave it off, because I know that wasn't his intention right there. But I do want to just make the point that our solution curve does not include the part that would be over here, over that infinite discontinuity. I mean, I guess it would have to be the x value that would actually, I think it's the cube root of 4, because it's the x value that makes the denominator 0. So, yeah. Yep. All right, I can't help myself. X is less than the cube root of 4. Cool. But again, that's not something that I've necessarily seen, something that you've had to do in anything. All righty. Number 2. Same thought process. We want to go through the point 2, 1. 2, 1 is right here. We should end up with this. Yeah, we should end up with a curve that looks like this. Another thing we have to be careful is our answer does need to be a function. So where this thing goes vertical and comes back the other way, we're only going to consider that top part right there. Because if I drew the curve, it would go like that. So, but it does say that y equals f of x, which means that we are a function. So once you stop being a function, we're going to lose that part to it. I'll write myself a note on this one to tighten this up a little bit. Okay, so we end up, again, the major part of this is doing this stuff. Dy dx, we've got 2x over y. So we're going to have y dy equals 2x dx. We'll integrate, which is going to give us y squared over 2 equals x squared plus c. Agreed? Multiply both sides by 2. That's going to give me y squared equals 2x squared plus c. Again, if you put that 2c there, you should end up with the same solution in the end. Your work will just look different in the middle. But it's any number in the world, so multiplying it by 2 doesn't change that fact. Square root both sides. You end up with y equals plus or minus the square root of 2x squared plus c. Yes. This, and now this one, now looking at what our answer is, this is the one where we will have to choose. When you have a plus or minus in your general solution and you go to write a particular solution, you have to choose whether it's positive or negative. That's going to be really easy to do because you're just going to plug the x in and see which one you need. And spoiler alert, since the f of 2 is positive 1, the only way to get positive 1 out of this function that I have written is to pick the positive 1. So I'll explain that when we hit the end there, but let's solve for the c first. So sure that goes all the way over there. So the f of 2 is 1. That means that f of 2 equals 1 equals plus or minus the square root of 2x squared plus c. But we'll plug our 2 in. 2 times 2 squared. So we've got 1 equals plus or minus 8 plus c. So there's a couple different ways to solve this. I could just kind of look at it and figure it out. That's kind of what I want to do, but I'll solve it. Square both sides. You get 1 squared equals 8 plus c. Let's do it this way. And then when you subtract, you get c equals -7. Okay. Which means that our answer is y equals, we'll leave it square root 2x squared minus 7. And then again, the thing is, the f of 2 has to give me 1. So I've got to choose the plus or minus there. If I put a minus there, the f of 2 isn't giving me 1. It's giving me -1. So we'll leave it as positive. Does that make sense? Right. So you've got to write a function as your answer. So you're not allowed to leave the plus or minus in the particular solution. A general solution, it's good because that's all the possible things that can happen. This is the one and only solution for f of 2 equals 1. Again, we'll pop over to Desmos real quick. Put that in, make sure it looks correct. Y equals square root of 2x squared minus 7. Again, we're only looking at the right-hand side of that curve. It does look like the curve goes a little bit more straight up than I had it drawn. But that is correct. All right, and our last example. Y of 0 is -1. We should get a curve that looks like this. This is an easy one to draw. Why don't you guys do this one? I think that's the best way to do it. Do it, we'll check it. And that's where we'll end it. So after some fun discussion, we came up with this as our final answer. Y equals e to the -1, e to the x minus 2. Which could also be written as e to the x minus 1 minus 2.
Please remain standing for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Don't miss that last part there. Like, I think that might be why this example is here. They brought that -1 back into the exponent of the first e. So e to the -1 times e to the x is e to the x minus 1.